So in this lecture, we are discussing regarding the power method of approximating the eigenvalues of matrix. So first we'll understand what is the power method, and then we'll do a programming for this power method. So might be in your linear algebra course, you have come across with if you have given A, which is a matrix of order n cross n, then to find out the eigenvalues of this matrix, you will able to solve the characteristic equation that is mode of A minus lambda I equal to 0. This is a characteristic equation, and the characteristic equation is of degree n because our matrix is of degree n. So lambda raised to n, Cn n minus 1, lambda raised to n minus 1, Cn minus 2, lambda raised to n minus 2, up to so on, C0 equal to 0 will be the characteristic equation, or I can say characteristic polynomial of this matrix A. For large value of n, that means your matrix is big, a polynomial equation like this, and it is difficult to solve and it's time consuming to solve such polynomials, because to find out the roots of this polynomial we need to deal with lots of programming, and it will be more difficult and more time consuming. So that's why a numerical technique to approximating the roots of polynomial equation for higher degree are sensitive to a rounding of error. And in this lecture, we will look at alternative method for approximating the eigenvalue. So what we'll present here is the method that can be used to find out the eigenvalue of a largest in absolute value, and that value it's called the dominant eigenvalue. So what we are going to discuss here is the problem of finding the largest, absolute largest value of the matrix, and that is known as dominant eigenvalue. And although this restriction may seem several, and dominant eigenvalues are primarily very interesting in many physical applications, and one of the applications I already talked that it is used into the page rank algorithms. So let us define what is the dominant eigenvalue and dominant eigenvector. So dominant means it is the largest in absolute. So let lambda 1, lambda 2 up to lambda n be the eigen values of a matrix A of order n by n. Lambda 1 it's called dominant eigenvalue of A if lambda 1 is bigger than modulus value of lambda 1 is bigger than modulus value of lambda I for every I running from 1 to n, and corresponding eigenvector to lambda 1 are called dominant eigenvectors of A. So the eigenvector corresponding to lambda 1 are called dominant eigenvector of A. So the largest eigenvalue, it is a strictly greater than for every value from 2 to n. Then it is known as dominant eigenvalue lambda 1, and the corresponding eigenvector is known as dominant eigenvector. So let us have the example and we'll understand that. For example, if I have a matrix A which is have 1 0 0 minus 1. Suppose this is the matrix we have. This is a 2 by 2 matrix. And we should note here very important things, that every matrix does not have dominant eigenvector. Value. Why? Because this matrix have two eigenvalue. This is a triangular matrix, and probably you have learned in your linear algebra course. If you have any triangular matrix is there, then the diagonal entries are eigenvalues of that matrix. So as per that, the eigenvalues of this matrix, lambda 1 is 1 and lambda 2 is minus 2. So these are the eigenvalue of a matrix A. R lambda 1 is this, lambda 2 is this. And as per the definition, this mode of lambda 1 is strictly greater than mode of lambda 2. It is not possible here because modulus will give only one value, 1 and 1, 1. So that's why this matrix does not have any dominant value. So the matrix A does not have dominant eigenvalue. Let's have the another example. Let's take this B equal to 2 to 1, and rest of the entries will consider as 0. So this is a 3 by 3 matrix. Here the eigenvalues of matrix B are 2, 2 and 1. Here is also, we cannot say that, because again with the similar argument as I did here, this matrix B does not have dominant eigenvalue. Let's have the another example, the third one, and that I'm defining C as a matrix 2 minus 12, 1 minus 5. See, this is not a triangular matrix, so you cannot talk about directly what will be the eigenvalue. You should find out what are the eigenvalues for this. So for that, we need to find out the characteristic equation or a characteristic polynomial is mode of C minus lambda I equal to 0. So that's for this mode is nothing but the determinant of C minus lambda I. So it is 2 minus lambda minus 12, 1 minus 5 minus lambda equal to 0. If you expand this determinant, this will gives me 2 minus lambda into minus 5 minus lambda plus 12 equal to 0. So if you multiply this two brackets, now that will gives me minus 10 minus 2 lambda plus 5 lambda plus lambda square plus 12 equal to 0. And if you simplify this, this will gives me lambda square plus 3 lambda plus 2 equal to 0. So therefore, the finally you will have lambda square plus 3 lambda plus 2 equal to 0. And if you can expand, or I can say will factorize them, it has two factors, that is lambda plus 1 and lambda plus 2. Because 2 2s are 1 and 2 plus 1 is 3. So therefore, lambda equal to minus 1 and minus 2 are the two eigenvalues for the matrix C. So what we can write, the eigenvalues of matrix C are minus 2 and minus 1. And you just observe that a modulus value of this lambda 2, that means this value 2 is bigger. So therefore, the minus 2 is a dominant eigenvalue for this matrix C. So what we can say, therefore, the dominant eigenvalues of the matrix C is minus 2, which is the highest in the modulus. Okay. Now, so this is the example of or how to find out the dominant eigenvalues for given problem. But our objective is to obtain the eigenvector also. And as per the definition, we know that the find out the eigenvector for lambda equal to minus 2. We start with Ax is equal to lambda x. So we'll have to find out what is this eigenvalue, eigenvector. So here it is Ax, we need to find out, but A is in place of A we have this matrix, that is 2 minus 2, 12, 1 minus 5 is the matrix. Let us consider this x is x1, x2. This is equal to lambda. The value of lambda is minus 2 we'll consider, and x is x1, x2. Ultimate goal is to obtain what will be the value of x1 and x2, non-zero value of x1 and x2. So that's why this will gives me 2x1 minus 12x2 equal to minus 2x1. If you simplify this two product of these two matrix, and if you equate this two matrix, then you will have this x1 minus 5x2 is equal to minus 2x2. So the first equation will gives me, if I take this quantity on the other side, so it will gives me 4x1 minus 12x2 equal to 0, and this will gives me x1 minus plus 7x2 equal to 0.
Minus 3x2.
Minus 3, yeah, minus 3x2 equal to 0. So you can take this 4 common out from this, then these two equations represent the same equation. So therefore we can have x1 is equal to minus 3x2. So the eigenvalue, or sorry, eigenvector, therefore the eigenvector of a matrix C corresponding to lambda equal to minus 2 is x1, x2, but the value of x1 we have calculated, it is minus 3x2. So it is minus 3x2 and x2. If I take this minus, why it is minus? It is plus, because x1 is equal to 3x2. So it is plus x2. So this will give me 3, 1, x2. So the eigenvalue, or sorry, eigenvector is this, provided this x2 is non-zero. So this will be the finding the dominant eigenvector. This is one method which you have probably learned in your linear algebra course. Here we need to discuss what is the power method. So in that we need to find out approximate eigenvalue in iterative manner. So first we'll assume that A has dominant eigenvalue with corresponding dominant eigenvector. So we'll assume that any matrix, some matrix A is there whose dominant eigenvalue is there and dominant eigenvector is there. Then we choose the initial approximation. So we'll start with the initial approximation with x0 of one of the dominant eigenvector of A, and this initial approximation must be non-zero. That means this x0 must be non-zero vector in Rn if your matrix is of order n cross n. So finally we have a sequence like this. X1 we can get by A is multiplying to x0. We'll get x2, which is ax1, which we have A into A of x0, because the value of x1 is A of x0. So you can have this is A square x0. So you will have x3, that is the third approximation, will gives me A of x2, that is A into A square of x0. So that will gives me A cube x0. And if you can go in this manner, at some stage, let's say kth stage, you will have xk is A into xk minus 1. So it is A into A power k minus 1 x0, and that will gives me A power k x0. And for large power of k, by property of scaling the sequences, we will see that we'll get a good approximation of dominant eigenvector of A. And this procedure we'll discuss in the next example, which we'll taking the same example in the previous one. So in the previous example, what we have did is we have calculated the dominant eigenvalue and vector. Here, by this power method, we'll calculate what is the dominant eigenvalue and vector for this matrix. So let us consider the matrix A with 2 minus 12, 1 minus 5. That is the same example which we have taken in the previous one. And we'll start with initial guessing, or you can take any, you can start with any non-zero vector, because it is a 2 by 2 matrix, so you can start with any non-zero vector. So being with initial guessing or initial start, initial non-zero vector, x0 is equal to, we'll start with 1, 1. Okay, you can take with any non-zero vector, you can start with. Now what we'll do is we find out iteration as we have did it here. So this is our x0 value we have started with. Now we need to calculate what is x1. To calculate x1, we'll do this a x0. So x1 is equal to a into x0. We already have a, that is 2 minus 12, 1 minus 5. If you multiply this with x0, that is 1, 1. Then this will gives me, if you do the product of this thing, things, that is gives me 2 minus 12, 1 minus 5. So this will gives me minus 10, minus 4. If we can common out minus 4 from this, so this will gives me minus 4 into 10 by 4. We will have 10 by 4, we can write down it is 2.5. So it is 2.5, and 4 by 4 will gives me 1. So we'll have this two things, that is 2.5 is here, that is 10 by 4, and 1. This is the first approximation. Now next, to find out x2. What is x2? It is ax1. We already have a, that is 2 minus 12, 1 minus 5. x1 we got, it is minus 10, minus 4. So we'll have this is x1, this is our x1. So we'll multiply this two now, that is minus 10 into minus 10 into 2, so that will is minus 20, minus 12 minus 4, that will gives me plus 36, 48, 12 4 are 48, minus 10 plus 20. So if you simplify this, this will gives me 28 upon 10. What is the max minimum value? Here you can take out. So you'll have 10 out. You will have it is 28 by 10, that we can write as 2.8, and this is 10 by 10, so we'll write as 1. Now we'll need to calculate x3, that is a of x2. That will gives me 2 minus 12, 1 minus 5, 28, 10, that is our x2. If you multiply this, will gives me 56 minus 120, because 2 into 28 minus 12 into 10, then it is 28 minus 50. So if we can just see that 120 minus 56 will gives me 64, so that will be minus 64, and 50 minus 28 will gives me 22, so this will gives me minus 22. So here the minimum value is minus 22, you can take out, so minus 22 into 64 upon 22, and 22 upon 22 is 1. 64 upon 22 will gives me, in calculator it will gives me 2.91. Okay, so this is the value you can have. This will gives me x3. Next we can have x4, that is gives me a into x3. So we'll have 2 into minus 12, 1 into minus 5. This is our matrix. The value of x3 is minus 64, 22. And if you multiply this, then this will gives me 128 plus 12 into 22. Can you calculate what is 12 into 22? And then here it is minus 64 plus 22 into 5.
Sir, 264, 12 into 20. 12 into 22.
12 into 22 is
264.
264, and 5 into 22 is
110.
110. So if you can subtract this 264 minus 128, will gives me 136, and 110 minus 64 will gives me 46. 46 is the minimum one you can take out. So you will have here it is 46, 136 upon 46, and 1. So 136 upon 46 will gives me
2.9565.
2.956. So it is 2.96. Okay, if I approximate by 2 decimal places, so it is 2.96. Previously it was 2.91. You just remember what was our correct vector was 331. This was our vector, and -2 is the eigenvalue. So we are actually approximating this eigenvector. You just observe. Now let's calculate x5, that is ax1 will gives me 2 minus 12, 1 minus 5, and this will be the value 136 into 46. If you simplify this, that is 2 into 136, how much? 6 2s are 12, 6 7,
272.
272 minus 12 into 46,
552.
552. And this is 136 minus 46 into 5. 46 into 5.
230.
230. So this will gives me 172 minus 150. It gives me minus 280. And this 230 minus 136 will gives me minus 94. So if you can common out this 94 from this, then minus 94 from this, then this will gives me 280 upon 94 and 1. So 280 upon 94 is
2.978.
978. So 78 is there, so that's why it is 2.98. We can approximate by 2 decimal places. So we'll have 2.98. Now let's do one more step, one more iteration. That is x6 is ax5 will gives me 2 minus 12, 1 minus 5, and that is x1, sorry, not x1 x2, but it is 2 minus 20, 280 and minus 94. So it is minus 280 minus 94 will gives me 2 into 280,
Minus
560.
560.
550,
60,
60,
60, sir. 60.
60 plus 12 into 94,
1128.
1128. Then minus 280 plus 94 into 5,
470.
470. So this will gives me 120, 1128 minus 560. It is gives me 568, and 470
190.
minus 280 is 190.
90.
If you can common out 190, which is the minimum one from this, then you will have it is 568 upon 191. So how much is 568 upon 190?
2.99.
2 point something, huh?
2.99. Okay, so here it is 2.98, 2.99. So in this manner, if we can go further, then we will have the dominant eigenvector, and it is approximating 3 1, that we can say from here. Okay, so the approximate dominant eigenvector we got is 3 1. Now once we got the dominant eigenvector, we need to calculate what will be the dominant eigenvalue. So we'll have one result for that to determine an eigenvalue from a eigenvector. So how to determine the eigenvalue from eigenvector? So for that, we'll have this result. If X is an eigenvector of a matrix A, then its corresponding eigenvalue is given by lambda is equal to A into X bar into X bar. This into means a dot product between these two vectors upon X bar dot X bar. And this quotient is called the Radiant quotient. That is the name of this quotient is Radiant quotient. And it is easy to see why this is the things, because you just see that if X bar is a eigen vector, then Ax bar is a lambda X bar. Dot product with X bar upon X bar dot X bar. So this quantity will have this. And lambda is a constant quantity, so that take out from this X bar dot X bar, and so we'll have lambda. So it is just slightly one line proof is there that this quotient will give me the value of lambda. Now here, if I want to find out what is the value of lambda in this case, we have this is the X bar. So we'll use that one. That is lambda into, sorry, if I want to calculate lambda, it is A into X bar upon X bar dot X bar. We have already A, so we'll calculate what is Ax bar dot X bar. So let's see that. We have A is 2 minus 12, 1 minus 5. So we're calculating what is Ax bar. X bar we have it is 3, 1. So that's why this will give me 2 3s are 6 minus 12, 3 minus 5. So this will give me minus 6 minus 2. This is A into X bar. So now lambda. So let's calculate Ax bar into dot X bar. That is minus 6 minus 2 dot product with 1, 3. That will give me minus 6 into 1. So that will give me minus 6. Minus 2 into 3. That will give me minus 6. So minus 6 is this. And what is X bar dot X bar? Sorry. This has to be a scalar quantity. So it is minus 6, so it will be minus 12. X bar dot X bar is 3, 1. Dot product with 3, 1. So it will give me 9 plus 1. That will give me 10. Okay, so this is lambda. That is Ax bar dot X bar upon X bar dot X bar will give me minus 12 upon 10. So it is minus. What will be the answer? Minus 12 upon 10. 1 point.
Minus 1.2.
1.2. Okay. Which is the approximate dominant eigenvalue you have? It has to be minus. So we have any calculation mistake is here? Because it has to be minus 2. the answer should be -2. Let us see that. 2 3s are 6, -12, 3 -5. 12 minus 6 is -2. 3 minus 5 is -2. Then it is 6 minus 6 minus 2. That is
Sir,
8. Yes.
instead of -12, there will be -36. 12 into 3. No, sir. It's okay.
12 into 3? No. 2 into 3 is
No, sir,
6.
no.
12 into 1, it is -12. So it is -6 is correct. 3, 3 into 1 is 3. 5 minus 5 into 1 is -5. So -2 is also correct. Now ax bar into x bar will be -6. So it is 6 into 1 will gives me 6. -6 and -2 into 3 will gives me -6. So this will be -12. This is x bar dot x bar will gives me 3 into 3.
Sir,
Yeah. Well, wait. We have to use not this 3 into 1. We have to use this value because that is our x. So it is 568 into 190 instead of 36. We should use that here. So this calculation is wrong. It is actually, what was the value? 568, 190. So 2 into 568, what will be that?
1136.
1136 minus 190 into 12.
2280.
2280 and 568 minus 190 into 5.
950.
950. So this will gives me 6, no, 4. 280 minus 1136. How much?
Minus 1144.
1144. And this one is 550 minus 568. 950 minus 568.
382.
382
Sir, minus 382.
minus 382. So A into X bar, that is this, into 568, 190. How much? The dot product of this two, that means this into this, so that is minus 1144 into 568 plus minus 382 into 190. How much is this? Minus, and this one is 568 square plus 190 square. Five 68 square plus 190 square will gives me
Sir,
3,
x
5,
bar
8.
into x bar is minus 722,372.
Minus 7.
22,372.
So this is minus 722,372 upon 358,724. 722,372 upon 358,7.
Sir, still 2 will not come.
2,724. 2.01 is coming.
Yes, sir.
So it is approximating our answer.
Okay.
Minus. So it is approximating answer, not correct answer. So it is approximation. Okay. So that is known as a power method. Let us do one more example. So it's known as a power method with scaling. Okay, so let's consider the one more example that have A is equal to 120 minus 212 131. So first of all, we'll start with initial guessing. We'll start with any initial vector x0. Here the x0 is a 3 by 3. This matrix is 3 by 3, so your x0 is 3 cross 1 matrix. So let us say it is 1 1 1. We'll starting with 1 1 1. So it is A into x0 will gives me 1 2 0 minus 2 1 2 1 3 1. If you product them, then we'll have 1 plus 2, it is 3, minus 2 plus 1 plus 2, that will gives me 1, 1 plus 3 plus 1, so that will gives me 5. So what is your x1? You just say that it is maximum value is 5. Either you can common out the maximum value or a minimum value. So maximum value is 5, so we'll take that 1 by 5 common. What is left is 3 by 5. 3 by 5 it is 0.60. That is 1 by 5 it is 0.2. And 5 by 5 it is 1. So we'll have this is the approximate first eigen vector. Same way we'll calculate x2, that is ax1. Now in the previous example what we have did, we have used the same vector, but now we are using the scaling vector. So here the scaling vector is this 0.06, 0.02, 1. So either you can use this vector or this one. Both will gives you the correct answer. Means approximate. And this method which we are doing here, it will gives me more accurate thing. So that's why what we'll do is we take this a x2. Sorry. We'll have x2 which is ax1, which we have 1 2 0 minus 2 1 2 1 3 1 is our matrix, and the approximate eigenvector we have calculated this 0.60, 0.2 1. So if you multiply this, then we'll have this value is, you just see that what will be the value we get. It is 0.60 plus 0.4 will gives me 1. Then 1.12 plus 0.2 plus 2. So it is also 1. And 1.63, it is to the 6.6, so it is 1.2 and plus 1, so it is 2.2. Here the maximum value, so your x2 will be 1 upon 2.2 is common out, maximum value is 2.2. 1 upon 2.1 upon 22 or 2.2 is 0.45. This is also 0.45 and here it is 1. So this is our next value. Same way you can calculate what is x3, that is a into x2. So can you tell me what is the answer of x3? So should you now able to do this example by your own?
Yes, sir, but only the last part is the lambda part where we add the values of lambda of x bar and multiply and find the value of lambda. So
Yeah,
that is the
that
otherwise.
also we can do. Okay, so x3 we can have here, it is 0.48. This we can have 555 and this is 1. Okay, let us have x4. x4 is 0.51. This is 0.51. This is 1. x5 we calculate, it is 0.50, 0.49 and 1. x6 we have 0.50, 0.50 and 1. And x7 is same as x6. So 0.50, 0.50 and 1. So that will give me what will be the eigenvector. So my x bar, the eigenvector is 0.5, 0.5, 1. So a into x bar, if I can calculate, what will get, that will give me the matrix A is 1 2 0 minus 2 1 2 1 3 1 into 0.5. I can write down 1 by 2 1 by 2 1. So that's why this will give me 1 by 2 plus 1 plus 0, that is minus 1 plus 1 by 2 plus 2, that is 1 by 2 plus 3 by 2 plus 1.
Sir,
Yes.
for x bar, at what decimal point should we stop to figure out our estimate?
You see, this is the 2 decimal places is enough. But if while you're doing in computer, that means if you are doing in programming, then your approximate will be more larger. But in computational, you can stop with 2 decimal places.
Okay, thank you, sir.
So this will give me 3 by 2, and this will give me 2 1 plus 1 by 2. This is also 3 by 2, and this will give me 3. Because this is 2 plus 1 3. So here this is the vector a into x bar. X bar is this. So we'll calculate now what is ax bar dot x bar. X bar is 3 by 2, 3 by 2, 3. This is 1 by 2, 1 by 2, 1. So this will give me 3 by 2 into 1 by 2 plus 3 by 2 into 1 by 2 plus 3. So this is gives me 3 by 4 plus 3 by 4 plus 3. So that will gives me 6 by 4 plus 3. So it is 6 plus 12 upon 4. So that will gives me 18 upon 4. So that will gives me 9 by 2. Okay. And what is x bar dot x bar? That is 1 by 2 square plus 1 by 2 square plus 1. So that's why it is 1 by 4 plus 1 by 4 plus 1. So it is 2 by 4 plus 1. So it is 3 by 2. So what is the lambda? That is a into x bar dot x bar upon x bar dot x bar will gives me ax bar will 9 by 2 This above value we have calculated 9 by 2, and this value we have calculated 3 by 2. So finally it is 3 is
3
the
as
answer.
value.
Yeah. So
But
the
there's your approximate value was 0.5, right?
where
So the x bar value, the final
no,
x
this
bar
is the
that we get.
eigenvector. See, this is the eigenvector, dominant
Yeah.
eigenvector,
Yes.
and this is the eigenvalue.
Okay. So it need not
So
necessarily be same.
eigenvalue is 3, and eigenvector, dominant eigenvector is 1 by 2, 1 by 2, 1. 0.5, 0.51. Okay, now I want that you guys can prepare a R programming for this problem. Proof of power method. That means if I give you, you can ask the user what will be the matrix. So user will enter the matrix, and then it will run that program, and the output of the program is what is the dominant eigenvalue and what is the dominant eigenvector. So that is the today's work we need to do. And there is a theorem which based on this theorem is work is known as the convergence of powers method. Why it this power method? That means why when you iteratively apply a to the x0 and then a square x0, then a cube x0. So ultimately you have to calculate what is a and x0. This will always converge to the eigenvector of the matrix. And this is a theoretically proved situation. Will not go into the detail of why it is true, but that is theoretical it is true, and it is the rate of convergence is very high. So with that, we'll move on to the R. And now your turn is to find out what will be the function, R function, to do this programming. Okay, so I will give you 10 minutes to do this. I think so in 10 minutes will be enough to make a programming for this or to have a function for this. Okay, so first let's have enter some matrix. Okay, in R. Let me share my way with you. Okay, so first we'll need to have our matrix. Let's say the matrix is any matrix you can enter. So matrix is C of 1 minus 3 2 4 4 minus 1 6 5 3, and columns will call it as 3, and row is 3. What is our A? A is this. So it is taking the value as a column. So I have entered the values of column 1 minus 3 2 4 4 minus 1 6 5 3. So this is our matrix. We'll start with first approximation, that is U0. We'll start with U0. U0 I'm taking as 1 1 1. So C of 1 1 1 is U0. Now we'll find out what is U1 by multiplying this A. But how to do the matrix multiplication? This is the command for that. Percentage star percentage U0. Okay. So that will gives me U1. So this is my first approximation. Is the 1164 is my first approximation. Now in that we need to calculate what will the maximum value, and we'll divide that. Okay. And that is our main value. So we can say that
Sir, can you please increase your font size?
okay, insert is in tool, global option, preference, appearance, is 24 18 24. Let us do that. Apply. Okay now.
Yes, sir.
Okay, so first I have entered A, and so what is A? Now A0 U0, which is our initial starting. Then we'll denote this is by some another vector V1, that is A into U0. So that is A into U0 is V1 is this 1164. Now we need to find out what will be the maximum value of 1164. That I can get by dividing by maximum value, and we'll call it that as U1 is V1 divided by maximum of U1. That is our first approximation of that. So that will gives me, so the what is the value of U1 is I have now? You can check 1 0.54 0.36. Okay, and whatever the maximum of this V1 will be your approximate eigenvector value. Okay, so the this is the first eigenvector approximation. This is, I can say, a first iteration. First iteration will gives me this. Now second iteration, that is, we'll say it is V2, which is the same as this procedure. A into U0, here it is U1. A percentage star percentage U2, U1 will have this V2. Then you calculate U2, which is V2 divided by maximum of V2. This is gives you second approximation, 1.01.04. You do this procedure. Okay. Now copy this. Instead of V2, you just write down V3. This is U2. This is V3. 3, 3, 3, and here is 3. And you just run that. So this is the third approximation. This is the third one. Okay, then you can calculate fourth. Paste. This will be V3 is used, so V4. This is V3. V4. 4, 4, 4, 4. This is the next one. Okay, and you proceed in that manner. Now we have a fifth. In similar manner. I have told you to make a function of this procedure. Okay, so try to make a function of this procedure. That is the objective. So in that manner, you can have further 6, 7 up to what. But it is better that you can make a function of this situation. So that can be done in just 2 lines. We'll have U, will make an empty vector. V is empty vector. We'll create V, which is empty vector. And we'll start with initially 1 with C of 1, 1, 1. Initial starting with that. Now we'll run a loop for I in 1 to 50. You can take as many as you can, but I'm fixing with 50. Running a loop. Okay. So V of I is A percentage star percentage U of I. Okay. Then U of I plus 1 will store as V of I divided by maximum of V of I. Then print maximum of V of I. So 5.7304 is the answer for this. You can have. You change your A, you can have this answer now. Okay, so this is the way you can do it. See, still you can modify this and you can make a function. For example, how much error you want, how much restriction you need, all sort of things you can do it here. For example, how many error, up to this much error I want my iteration should run. That that situation also you can put it in the if loop, sorry, if condition, and so you want to try for that also. For example, your function error this will be this much, and then my algorithm will be stopped. So that also you can do it. You can use the without iteration. Also, you can do the power method without iteration. I don't want to use the iteration, and then also we can do that. There are many ways to do this. First one we have did it. Let us have, let's make a function power rm. We'll make a function. So we have a x0 need to enter, and the thresh, that means how much error you need. Okay, then we'll enter what is m0. m0 is equal to x0.
So your screen is not visible in case you are showing.
Yeah. So we'll make a function, this power rm function. Function have three attributes, a, x0, and thresh. Then we'll fix one first value m0, that is x0 of which of maximum its absolute value of x0. So whatever the absolute value of that will show here. Then it will calculate x1 will equal to a percentage star percentage, that will multiply with x0 divided by m0. Then m1 it will calculate x1 of which dot maximum of absolute values of x1. Then this is a cat function m1 slash n, that will gives you new line. Okay, if absolute value of m1 minus m0 is less than thresh, okay, then you need to stop, then return m1, else power m, otherwise you will just run this a x1 thresh. Okay, and this will finish your function. Now we already have a, that is this. we already have x0, which we have denoted as u0. We need to fix our thresh. Thresh you can have any other value. So now we'll run this power m. A u0. Let's say thresh is 0.001. Oh, I have not run the function. Fine. So 5.7302. Previously it was 37347 there. But here we have put it this iteration. That means go up to this much error. So it will have shown this value. This is without using for loop. We have did this. Okay. You can use while statement also here. Okay. You may use while statement. Then